Our lessons so far have been about what functions are and how to represent them. So in Lesson 7.3, we are going to talk about what linear functions are. So our objective is to classify a linear function as a rule defined by y equals mx plus b, whose graph is a straight line. So the key concept is about the rate of change. A linear function is a function that has a constant rate of change. So that's important there that you highlight that it is a constant rate of change. Its graph will form a straight line. Now, down here we have the definition of slope, and we have three different ways to think about slope. So slope is the vertical change over the horizontal change. It is y2 minus y1 over x2 minus x1. And remember that rate of change and slope mean the same thing, so the rate of change is the vertical change over the horizontal change, just like it was over here. Now, an extremely important concept is this next line. All linear functions have a constant rate of change and can be modeled by a straight line. The word constant means the same, so it changes the same amount each time. Now let's examine this part 1 about representations. The set of ordered pairs given are all graphed right here. Because all the points are in a straight line and the rate of change is the same between all points, they all go up and over the same amount. This is a linear function. Now we're going to see if you understand what we've done with another example. So in this next example, we want to know if the set of ordered pairs represents a linear function. So we would go ahead and graph or plot those points, see if they form a straight line. If they do, then it's a linear function. So I'm going to go ahead and plot all of those points now. You should do the same. Pause the video and see if you were right. Now it's a little difficult to see the grid on this copy, but you can see that I have my points there, and I can connect them with a straight line. So therefore, this is a linear function. I can draw a line that goes through all those points, and it's a straight line, so this is a linear function. Now I should know if it's a linear function, then the rate of change is constant. So if you look at the change in the y values, here's my first y value and here's my second one. So that goes up 3, while the x's go up 1. So that's up 3 over 1. The second one, we have between this point and this point, the y values go up 3 and the x values go up 1. So that again is 3 over 1 right here. This next set of points, these two, we go from 5 to 8 is up 3, and from 3 to 4 is up 1. So it's 3 over 1. That is a constant rate of change. And that rate of change is 3, which is what we figured out over here. In part 2, we talk about using tables to identify linear functions. So the tables can be used to represent linear functions as well as graphs, and we must go back to this idea of having a constant rate of change. So we're going to look at the change in the y's, or the outputs, compared to the change in the x's, or the inputs. So here you can see that all the the y's go up 3, up 3, up 3, while all the x's go up 1. So the rate of change is 3 over 1. Since the rate of change is constant, each input has exactly one output. It represents a linear because the rate of change was constant, function because every x has exactly one y. So now let's talk about this example. There are two parts to it. Does the following table represent a linear function? And here's a reminder. The rate of change between each point, or each input and output, needs to be the same in order for it to be a linear function. So now what we're going to do is we're going to look at the change in outputs. So from 2 to 4 goes up 2, and from 0 to 1, change in inputs, that's 1. So it's 2 over 1 there. We need to continue to look at the table throughout the whole thing. So if you look from 4 to 7, it goes up 3, and then from 1 to 2, it goes up 1. So that rate of change is 3 over 1. And I can stop right there. This is not a linear function because the rate of change, 2 over 1, is not equal to 3 over 1. So it's not a constant rate of change. The rate of change is not the same. So therefore, this table does not represent a linear function. Let's move over to part B. So we're going to look at the change in outputs compared to the change in inputs. So the change in outputs goes up 1. The change in inputs goes up 3. So that rate of change is 1 over 3. This one goes up 2, and this goes up 3. So that rate of change is 2 over 3. Because 1 over 3 is not equal to 2 over 3, this is not a linear function. Let's take a look at the next example. So does the relation defined by the table represent a linear function? So we're going to look at the change in outputs. So this time it goes down 3. Compared to the change in inputs, that goes up 5. So the rate of change there is negative 3 over 5. From 5 to 2 goes down 3. And from negative 5 to 0, that goes up 5. So that's negative 3 over 5. So far, so good. 2 to negative 1 goes down 3. 0 to 5 goes up 5. So that's negative 3 over 5. That's good. And negative 1 to negative 4 is down 3. 5 to 10 is up 5. So that's good. Now I'm going to go ahead and extend this a little bit. What if I go to negative 10 here, and over here I'm going to go to 20. So if I do that, that goes down 6. So it looks like it might not work. And over here, it doesn't go up 5, it goes up 10. So what we have to do is we have to compare negative 6 over 10 to negative 3 over 5. And when I do that, I should recognize that those are equal. Negative 3 over 5 will simplify, negative 6 over 10 will simplify to negative 3 over 5. So that does work. So yes, this is a linear function. It's linear because the rate of change is constant, and it's a function because if I look at all of my inputs, they don't repeat. Every single input is paired with exactly one output, so that's a function. Let's move on to the next page. Part 3, we are still using tables to identify linear functions, and you can use linear functions to model situations, make predictions, or draw conclusions. Let's take a look at the example about the scuba diver. It says when the scuba diver goes underwater, the weight of the water puts pressure on the diver. The table shows the pressure on the diver increases as the depth increases. So we're looking right here. The deeper you go, the more pressure you have. What is the rate of change of this linear function, and what does it represent? So if I take a look at the change here, it goes up 4.4, while this goes up 10. So the rate of change is 4.4 over 10. Now we don't typically write a rate of change with a decimal and a fraction together. So what I'm going to do is I'm going to put 4.4 over 10, so I know that that's how I came up with the numbers, but then I'm going to write an equivalent statement to that. So 4.4 over 10 is equal to 11 over 25. So what does that mean? Remember that the top number was about the water pressure. So that's pounds per square inch. That's how we read that label, pounds per square inch. So it goes up 11 pounds per square inch for every 25 feet, and I'm getting that from here, for every 25 feet that you dive. So I'm going to put that into words over here. The next part asks us to use that rate of change to predict the water pressure on a diver at a depth of 60 feet and then at a depth of 100 feet. So I will say the 60 feet is the easier one to do. If I take a look at this table, the next number is going to be 50, and then after that it's going to be 60. So I could just easily increase my values over here and then follow the pattern. So I'll start with that. So what I've done is I increased this 10, so that means this increased 4.4, following this pattern in the table, and I increase another 10, and that increases another 4.4. So that tells me that there are 26.4 pounds per square inch of water pressure when you dive 60 feet. So again, that says 26.4 pounds per square inch. That's how you read that label, pounds per square inch. Now, how about the 100 feet? So if I keep going up by tens, it's going to take me a little bit. I can go ahead and jump. So if this jumps to 100, that actually jumps to 40 spaces. So if I go here to 100, which is what I want, that goes up 40. So over here, I would have to go up 4 times as much. Now I'm getting 4 times as much because this went up by 10, this went up by 40, so that's 4 times as much. So it goes up 4 times as much as this does. So 4.4 times 4 is 17.6. So we need to add 17.6 to that. And that results in 44 pounds per square inch. So the water pressure is 44 pounds per square inch. All right, let's take a look at the last example now. This time we're talking about the length of a shark after so many years. So as the age increases, so does the length. We want to look for a pattern. So if we take a look at how much it grows here, it goes up 3.75. It goes up 3.75 here, and it goes up 5 here. So let's go ahead and write that in. So it goes up 3.75, and the x values go up 5. Does that pattern continue throughout? So 44.5 to 48.25, we go up 3.75. And here we go up 5, so that pattern works. And 48.25 plus 3.75 is 52. So this one goes up 5. So the rate of change is 3.75 over 5. Now again, we don't keep fractions and decimals inside of each other. So 3.75 over 5 is equivalent to 3/4 or 0.75. You could write it as a decimal or a fraction. I'm going to choose to write it as a decimal. So let's talk about what that means. We took the length in centimeters over the time in years. So what we just found was the growth of 0.75 centimeters each year. That's what the rate of change represents. Let's put that in writing. Now let's figure out the length of the shark at 25 years old and then at 40 years old. So 25 is easier. We just continue the pattern, add 5 more years there, which means we would just add 3.75 over here, and then we would get 55.75. So that's an easier one. So the length of the shark at 25 years old is 55.75 centimeters. Now to get to 40 we have to jump a bit. So to get to 40 we actually go up 15 there, which is 3 times as much as what we have been doing. So I would have to go 3 times as much over here. So 3.75 times 3 is 11.25. So I go up 11.25 from 55.75, and that equals 67. So when the shark is 40 years old, we could expect that shark to be 67 centimeters. And that is the end of the notes.